Hello everyone, this is D. Swati from Aeronautical Engineering. My roll number is 23951E2153, and today I have a subject called Physics, my Tech Talk topic. It is conducted by the faculty name Mr. Santosh Singh. So now move on to the topic of the Tech Talk. Okay. So today's Tech Talk topic is crystal lattice parametric identification based on analysis of isosurface configuration. So let's start the topic of today's Tech Talk. So first one, crystal lattice. What is about the crystal lattice? So we have to discuss today on this crystal lattice. So crystal lattice parametrically identification based on analysis of isosurface configuration is a complex yet crucial process in materials science and solid state physics. This lattice parametry including lattice and constants of angles play a fundamental role in determining various properties of crystalline materials such as electronic or optical or mechanical properties of it. Isosurfaces which represent regions of constant values in three-dimensional scalar field provide very valuable insights into the spatial distribution of physical properties within a crystal lattice. So as you can see in the figure, it shows how the crystal lattice is made and how it's performing. Now properties. To begin with, the analysis involves generating isosurface of different physical properties such as electrodensity or phonodispersion within the crystal lattice. These isosurfaces are then examined to identify characteristics, features and patterns. As you can see in the figure how the pattern is made and how its surface and how its characteristics are defined. Then that corresponds to specific lattice parameters and for intents and various variations way shape and orientation. It has many of it. So of a isosurface can indicate changes in lattice constant or angles and many more of them. Okay, algorithms of lattice. We can see the algorithms how it is converted in by stage and how it's converting as shown in the figure. Furthermore, machine learning algorithms and data driven approaches are increasingly being utilized to analyze isosurface configuration and exact revealed information about lattice parameters by training models on large dimensions for simulate or experimental isosurfaces. These algorithms can learn to recognize patterns and correlations that may not be immediately apparent to human observations and other observations. It can increasing by utilizing to analyze that isosurface configuration. So it has an algorithm and data driven. It approaches both data and algorithm and furthermore many of the things as shown in the figure. Analysis. Additionally, the identification of lattice parameters from isosurface analysis requires careful validation and comparison with experimental data. This may involve fitting, simulating isosurfaces to experimental measurements obtained from techniques such as X-ray diffraction or electrons microscopes and adjusting the parameters until a satisfactory agreement is reached. Till that point, as shown in the figure, we can see there are 3 points which are ZA, ZB and ZB, and which is has a mirror one. We can see the again ZA. It has a parallel line in which we had constructed a lattice in those one. Okay. Lattice defects. Moreover, the accuracy and reliability of a parametric identification process depends on various factors including the quality of the input data, the choice of compositional methods, and the complexity of the crystal lattice under study. In some cases, it may be necessary to condition additional factors such as lattice defects or structural distortion, which can affect the interpretation of isosurface configuration. You can see, as we can see that in the diagram, we have some of the balls, like it's like a constant particles which are having the same shape, same size, and it's form a crystal lattice in that. And in the moreover accuracy, the parametric identification process, and it has various factors including the quality of the input data, so computational methods and complexity functions. Furthermore, the parametric identifications of crystal lattice based on isosurface analysis is not limited to static structures but can also extend it to dynamic systems such as phenomena models and thermal fluctuations. By analyzing and evolution of isosurface under different conditions, researchers can gain insight into the behavior of lattice parameters such as functions of temperature, pressures, or external stimuli. As shown in the figure, we can see a cube. In that, we have some of the points, some of the 3 points like 1, 2, 3. As that points are given a specific number by combining some of the numbers. At last, we don't have any number to combine that, as it's a unit point for over it. And we have 2D representations. It has a 1D, 2D, and 3D, and it has some of the representation. For this topic, we have 2D representation. Additionally, the development of advanced visualization techniques such as interactive three-dimensional rendering and virtual reality environment can facilitate the interpretation of complex isosurface configuration. These tools enable researchers to interactively manipulate and analyze isosurface, facilitating the identification of stable features and correlations they may overlooked in traditionally two-dimensional representation. As in the diagram, we can see the 2D pictures which are having some of the specific points and some of their specific units in it. Integration of isosurface. Furthermore, the integration of isosurface analysis with other calculations and experimental techniques such as intro calculations and spectroscopic measurements offers comparisons approaches are characterizing and understanding the properties of crystalline materials by combining multiple sources of information. Researchers can enhance the accuracy and reliability of lattice parameter uh, identification and gain deeper insights into underlying physics governing to behavior of materials at the atomic scale. It has specific amount of scales in which we have to make it more. Okay, as for the diagram, we can see a pure metal crystal green atomic lattice. It in the pure metal we have a crystals. In that we are gaining atomic lattice. Some of the parts in that surface, it's known as isosurface. In that we can see the lattice how they are formed. Okay, in some of the conclusions, crystal lattice parametric identification based on the analysis of isosurface configuration represents a multifaceted approach that leverages computation, modeling, machines learning, and experimental validation to unravel the intricate properties of crystalline materials by examining the spiritual distribution of physical properties within the lattice through isosurface. Researchers can extract valuable information about lattice parameters such as constant and angles. The process involves generating isosurface for various physical properties employing uh, computer techniques like density, frictional theory, and modular dynamics, simulation, and utilizing machines learning algorithms and pattern recognition. It has recognition, validation against experimental data and consideration of factors with lattice defect and dynamic behavior are crucially and ensuring accuracy and reliability of the identified parameters in it. So in isosurface, we can see furthermore the integration of isosurface analysis with other computation experimental techniques such as initio calculation, spectroscopic measurements. Some of it has specific properties of crystalline materials and many more. By combining multiple sources, multiple methods, we can construct a lattice by combining some of the metals. Like if you have a pure metal, it has a crystal, and in that crystal we have present many types of lattice like space lattice, atomic lattice, and many more ion lattice. So in this we can gain the lots of lattices surfaces in the crystal, which has we can find in normally in metals and some other places also. At the conclusionly, lastly, we are saying the crystal lattice parameters identification based on the analysis of isosurface configuration. It's the main process of uh, finding a lattice. A crystal lattice is the isosurface configuration. It represents a multifaceted approaches that leverages commercial modeling, machine learning, and experimental validation and unreal interpret properties. So at the last, this process involves generating isosurfaces of various physical properties. As we know that simulations utilizing machine learning algorithms of pattern recognition, validation, employing molecular dynamics, function theory, and some of the experimental data and consideration of factors like lattice defects and dynamic behavior, crucial enduring and accuracy and reliability of identification mathematics, and some of them are like. So at last, thank you for this session. So thank you so much.